So section 4.3, it's going to be on solving rational equations and inequalities. And the kind of overall goal is going to be to get rid of fractions. If we can take a problem that has fractions and get rid of it, it gets easier. Okay, mostly we're going to focus on algebra. We will do a little bit graphically, but nothing by hand. Okay, it's all going to be on the calculator. So the first problem we're going to look at, it's going to use the distance, rate, and time formula. So if you don't know or remember what that is, it's distance equals rate times time, where d is a distance, r is a speed, and t is a time. All right, so this problem, basically it's going to be about a person traveling, and they're going to use two modes of transportation to get where they're going. So it says Sue drove 30 miles to the train station, got on the train, and the total journey was 120 miles. It says the average rate of the train was 20 miles per hour faster than the car. All right, so that's everything that we need to know to set up what we're going to do. What we're going to do is write a formula for the time it takes to complete the trip as a function of the speed of one of those things. I think we're going to do it relative to the speed of the car. So if we're going to do it relative to the speed of the car, and we don't know the speed of the car, how could we represent that for now? Yeah, we'll use x to represent the speed of the car. You could also do this from the perspective of the speed of the train, but we're doing it from the car. Now, they want us to write a formula for the total time of the trip. How many different modes of transportation is Sue taking? Yep.
Two.
Yeah, she's taking 2. Now, what we want to do is think about this formula. Distance equals rate times time. And if you solve it for t, what do you get? Yeah.
You get distance divided by the rate.
Yep, you get distance divided by rate. So the big idea of what we're doing is the total time equals the time she spends in the car plus the time she's on the train. So that's what we need to translate into an equation. And our time is going to be a function of x. So we're going to write the time as a function of x. Now the time in the car is the distance in the car divided by the speed of the car. What's the distance that she traveled in the car? Yeah?
30 miles.
30 miles. And then distance divided by rate will give us time. What's the speed of the car? Yeah? X. Now we need the time on the train. So first thing I need is the distance that she traveled on the train. Yeah?
The distance is 90 because it's 120 subtracted by 30.
Right. They told us the total journey was 120 miles. And what's the speed of the train relative to the car? Yep.
Would it be x plus 20?
Be x plus 20. So there's a formula that represents the time it takes to complete the trip. You tell me the speed of the car, could fill it in for x, and now you got the time. Any question on the formula? You would need to know the distance equals rate times time. So if you don't know it, well, now you do. Distance equals rate times time. Okay, so now they want us to look at that and do a little bit of what we did last week. We're not graphing by hand. Just find the asymptotes, the zeros, the EBM, and then we'll use the calculator to sketch it. It is going to be helpful to put those together in order to find the EBM. Because the EBM is the highest degree term in the top divided by the bottom. But to put these together, what do I need to have if I want them together as one fraction? Yeah. Right. And the easiest way is to just multiply the two together. What is the fraction on the left missing in the denominator to make it the common denominator? Yeah.
The top of it is missing the x plus 20.
Yeah, so we're going to multiply by x plus 20 over x plus 20. And what's the fraction on the right missing? So that that denominator is the common denominator. Yeah, it's missing an x. So here we're going to end up with 30x plus 600. I'm going to put that up here because I'm going to have some like terms. So I get 30x plus 600, and then 90 times x is 90x. Okay, so what would my numerator be when I combine like terms?
120x plus 600.
Yep. Now you don't have to combine it to do everything. I could have done the asymptotes the way it was, but the EDM it helps to combine it. Okay, you'll see why. Okay, so let's start with the EDM. Okay, what's the highest degree term in the top? Yeah.
120.
Right, the highest degree term is the 120x, which you couldn't really see till you combine them. And just be careful, what's the highest degree term in the bottom? Yeah. X squared, you have to FOIL that out. And that's going to turn into 120 over x. There's your EDM. Now, the horizontal asymptote uses the EDM. You let x get what in the EDM, and it tells you the horizontal asymptote. Let it get bigger and bigger. What happens to what's in that box as x gets bigger and bigger? What does the value in the box get close to? Yeah? 0. Yeah, it gets very close to 0. So there's your horizontal. Let's see, vertical asymptotes. Does anybody remember how you find the verticals? It's where
Zeros of the denominator.
zeros of the denominator, so 0 and negative 20. I'm not saying negative 20 makes sense in a problem where x represents the speed of the car, but this didn't say anything about the speed of the car. It just said to find all that stuff. So there's your verticals. Anything else they want? Asymptotes? Oh, the zeros. So the 0 is where it crosses which axis? These are your roots. Yeah?
Yeah.
Right. It's where it crosses the x-axis. To find an x-intercept, you set y equal to 0. Well, I don't really have a y up here, but what symbol represents y? Yeah?
T of x.
T of x. Set that equal to 0. And it's going to be easier to use the combined fraction. So if you set this fraction equal to 0, what's the only way that a fraction can equal 0? Yeah.
If you're going to solve this quadratic thing,
No quadratic. You won't have to do a quadratic here.
if all the x's equal 0,
If you plug in 0 for x, you're finding the y-intercept.
yes.
We want the x-intercept when the numerator equals 0. So the only way that that fraction can equal 0 is when the top equals 0. So set the top equal to 0.
It's negative 5.
Let's see, minus the 600, plus you divide by 120. Yep, it would be negative 5. Again, maybe that doesn't make sense in this word problem because it's about the speed of the car, but that's your x-intercept. Good. Okay, and find a complete graph. Okay, let's graph. Now, they didn't say to find a graph of the problem situation. I would say if we were doing that, we want to be careful about negative values for the speed and the time. But in this case, we're going to use all the values we can. So type it in, 120x plus 600 divided by, I'm going to FOIL that so I don't have to put in the extra set of parentheses. X squared plus 20x. So there's your fraction. We've got a vertical asymptote at negative 20, so I would go, I don't know, you could do like negative 30 maybe. X max is the maximum speed of the car. We could go maybe look up to 75 and see what it looks like. All right, let's try graph and just see what it looks like. Well, I'm just barely, I noticed something in the lower left. You probably can't see it that well. It looks like there's a blue dot there. So there's another part of this graph that I'm not seeing. Okay, when you have vertical asymptotes, usually you have one more pieces of graph than vertical asymptotes. We have 2 vertical asymptotes. That means you should have 3 pieces of graph. So let's set the, I don't know how much further we have to go. Let's try negative 40 and maybe negative 35. I know there's a third piece, and there it is. That's good. I would say that's a good complete graph that shows the vertical asymptotes, and it shows all 3 pieces. If you want to set Ymax a little higher, I mean, you could, but you're not going to see anything interesting. Both those pieces are just going to keep going up.
We still need to show the full thing when it's asking us to show the choose a window that shows the full solution, even for equations or problems where negative stuff doesn't make sense, or like
Yes.
showing it doesn't make sense. We still need to show the full thing with all the transformations.
Yep.
Okay.
So, yep, showing a complete graph of that equation.
The image that you have is blocking.
Yeah, it's blocking the negative. I know, it just does that sometimes. Thank you. Negative 40. And there's other windows, but I'd say that's a decent window. Now, what would we want to set to 0 if we were just looking at this in terms of the word problem? Negatives wouldn't make sense for which 2? Yep.
You'd want the minimums to be 0.
Yeah. You wouldn't want to have negative speed if you were looking at this in the context of the word problem, and you wouldn't want to have negative time. So essentially, we're going to be focusing in on what quadrant if we graph this in terms of the car problem.
Quadrant 1.
You're really just looking at quadrant 1, which looks like that. There's the speed of the trip, and notice the speed gets less and less as, well, the time gets less and less as the speed gets higher. But the time will never reach what?
0.
Right, it can't reach 0. It's impossible, even if it was 500 miles an hour. It's impossible for the time to hit 0 because that's an asymptote. And realistically, you can't do something in 0 amount of time. All right, any questions on the window? Right, now, they said that Sue has 2 hours to complete the trip. Find the speed she has to travel. Let's just do it graphically. We're going to do a lot algebraically. So let's use the calculator and just do it graphically. Okay. So if she has 2 hours to complete the trip, what do I need to add to that graph to help me figure this out? Yep.
Set y equals 2.
Yeah, set a line at y equals 2. That's going to mark the 2 hour time. And what would I do now?
Wouldn't it be actually not 2, but
No, it would be 2. Yeah. Because our speed was in miles per hour. Now, if the speed was in like some different unit, like miles per minute, well, now we got a problem. Because now we're using minutes and we're mixing hours. You got to keep the units the same. But in this case, that's good. So we got 2. And what do I have to do now?
Find the range, you said.
Yeah, find where they intersect. And this tells me exactly if she could complete the trip in 2 hours, then x is 46.46. But what was x? The speed of the car. So that means the speed of the train would be how much?
Well, the speed of the train would be 60.
66.46. So just be careful if you get all the way to this point. Pay attention to what they're asking for: the speed of the train or the car. In this case, they want to know the speed she must travel by car. So it is 46.46. Well, approximately. So any question on solving that graphically? You're going to be able to solve that equation algebraically when I show you the next piece.
For speed of the car and speed of the train, if we're given their exact, could we potentially be faced with a problem where we're given the two speeds and we're given like a final distance, and we need to solve like each what each one covered? Like, you know what I'm talking about? Like 30x plus 50y equals 12,000, and then like solving that out.
It's going to be like that.
In this in this unit, could we possibly be?
No, it's going to always be like that. We're going to do another one like that. I'm just going to change the time to like 1 hour and 40 minutes. But it's still going to be the same type of thing you're solving for. Yep. Okay, so we didn't actually do this because we did it graphically. Let me just change how to word that. Okay, so let's write down multiplying both sides of an multiplying both sides. Let's change this to of an expression. So multiplying both sides of an expression by a variable, comma, this may result in an equation not equivalent to the original equation. Perfect. So when we start to solve these algebraically, we're going to have to multiply both sides by a variable. And when we do that, it can mess up the answers. So what can happen is we get an answer that's extraneous. Okay, when you multiply both sides of an equation by a variable, you can get an answer that is extraneous. What that means is it's an answer that works because you multiply both sides by a variable, but it does not work in the original problem. Right, and I'll show you an example. So the only way to detect an extraneous answer is to check it. Okay, you plug it back in and see if it works. Let's say we had x plus 2 equals 5. So x equals 3. Does everyone agree with 3 as the answer to that? Is there any other answer besides 3?
No.
Well, let's do something a little different. Let's just multiply both sides by x to start. So we get x squared plus 2x equals 5x. Did I correctly multiply both sides by x?
Yes.
Okay. Then let's solve it now like a quadratic and bring everything to one side. So x squared plus 2 plus, what would that be on the left if I bring the 5x over?
Wouldn't it be minus 3?
Yeah. So it would be minus 3x equals 0. Oh, I had another one I was going to show you. And now what can you factor out on the left? Yep, so we could factor out an x. And Lily, what would make the first factor 0? Or what would make the second factor 0? 3, yep. So x equals 3 would make this one 0. How about this one?
0.
0. Does everyone agree those are the two answers to that problem? Now, was 0 a solution to the original?
No.
No. So by multiplying both sides by x, I created an extra answer in the problem that shouldn't have been there. Okay, it's called extraneous. Now, when you're solving x plus 2 equals 5, you never multiply both sides by x. That's not how you do it. But in the ones we're going to do, that is how you do it. You've got to multiply both sides by a variable. So always go back and check. And if you get an extraneous answer, cross it out. Okay. I might even ask you on the test something like, I want you to solve this problem. And in this box, put the answers that work. In this box, put the extraneous answers. There's no way to get the extraneous answer without doing the whole problem. The graphing calculator can't give it to you. Even if you graph it, it doesn't give it to you. All right. So the reason you're going to have to multiply by a variable is because the goal is going to be to get rid of anything that's in the denominator. So let's look at an equation first that's just numbers, and then we'll try it with letters. Let's say we have 3/4 plus x over 3 equals 5/12. And the only thing that really makes that equation a little bit more challenging is all the fractions. So if we could multiply everything by the same thing and cancel out all the denominators, this gets a lot easier. Does anybody see what we could multiply everything by? And it would cancel all my denominators. Yeah.
You multiply everything by 4 times 3.
Yeah. Multiply everything by 4 times 3. And I'm going to do it a certain way because I want you to see what happens. I'm going to multiply this by 4 times 3, 4 times 3, and 4 times 3, which is 12. What's going to cancel in the first fraction when I take 3 divided by 4 times 4 times 3? Yeah, the 4 is going to cancel. What's going to cancel in the second fraction? 3. And the third fraction? The whole thing. That's exactly what's going to happen when we do this with letters. Exactly like that. And now we have numbers. So 3 times 3 is 9. This is positive x times 4. And on the other side, it's just 5. That's a much easier equation to solve than what we started with. But that's the general idea. Any questions how I got rid of my denominator? I'm not going to finish that, but we're now going to do the same thing, but we're going to do it with letters. If you wanted to finish it, I think it's -1. -1 is the answer. All right, let's try it here. So in that last problem, what we multiplied by was the LCD. And the least common denominator, in general, it's going to be the product of the two that you have right there. Because this number is going to be also the product of the two you have right there. In general, it doesn't have to be. Like this number could have been a 13 or it could have been anything. But it's the ones I give you, it's going to be a little bit easier. Okay? This number will always be the product of those two. You should always check that, make sure it's true. But in general, that should always happen. So how could I check that x squared minus 4x plus 3 is the product of those two? What could I do with the x squared minus 4x? Yeah.
You could factor it out.
Yeah, let's just factor it. And the first term would have to be an x and an x.
Both negative.
They both have to be negative because you have a negative in the middle and a positive at the end. And then two numbers that multiply to give me 3.
3 and 1.
3 and 1. So it's x squared minus 4x plus 3. Perfect. So the denominator on the right is the product of the two on the left. So now I'm going to ask the same question I asked when we did the other one. What are you going to multiply all three of those by to get rid of your denominator? Yeah.
The same vectors, 8x minus 1 and x minus 3.
Right. Instead of having a number and a number as the factors, it's going to be a binomial and a binomial. Okay, so it's x minus 1, x minus 3. There. There. And here. Now don't FOIL out x minus 1, x minus 3, because something's going to cancel in each one. What cancels in the first one?
X minus 1.
That's gone. And the second one?
X minus 3.
And the third one?
The entire denominator.
Entire denominator cancels. So all you're left with is a 2 on the right. And now you have to distribute that out. What's 2x times x minus 3? 2x squared minus 6x. Now here's where you got to be careful. You're distributing a positive 1. If that was a negative, that negative goes with the 1. Okay. In this case, it's just a positive 1, so nothing really happens. It's just x minus 1 equals 2. And now that's a quadratic. So what do we generally try to get a quadratic equal to when we solve it?
0.
Get it equal to 0. So 2x squared minus 5x minus 3. And now let's see if we can factor it. If we can't, what are we going to have to use?
Quadratic
We're
formula.
going to have to use quadratic formula, but I think it's going to factor. What would my first terms be?
X and then 2x.
So yeah, 2x and an x. We got a negative constant, so that
Plus
means
minus.
you got to have a plus minus. I would try it like that. Maybe. Yeah, I think that's going to work. And then two numbers that multiply to give me 3.
3 and 1.
3 and 1. Let's check it.
What?
One second.
Random timeout.
Okay, so what did we say? A 3 and a
3 and a 1.
A 3 and a 1? Oh, we gotta check it. 2x squared minus 6 plus 1 is minus 5. Perfect. Okay, so now, what would you plug in to make x 0 in the first factor?
0. Oh, wait, no.
Negative 1/2, yep. And what would you plug in for the second factor? 3. Now, we have to check if we have an extraneous answer. The quick way to tell that it's extraneous is it causes you to divide by 0. If that happens, you need to cross it out. Let's check the 3. Can you plug 3 back into the original problem? No. If you try to plug in a 3, you're going to divide by 0. That means 3 is extraneous.
Wait, earlier you were saying you have to like multiply it to everything.
So we did multiply both sides by an expression with a variable in this case.
Oh.
X
oh,
minus
that's
1,
right.
x minus 3. Since we had a variable in what we multiplied, that's why that happened.
Oh.
But there was no other way to get rid of those denominators. So we had to. Now, how about negative 1/2?
It doesn't interfere because we have a minus 1.
Yeah, the only answers that would be extraneous here are 1 and 3. We got 3, so we cross it out. And the other answer is 1. But that's not 1, that's negative 1/2. So that answer is fine. So there's 3 things that can happen when you solve these problems. One answer works, one answer doesn't. Both answers could work, or both answers could be extraneous. Those are the three things that could happen.
When none of them work, you just put
You just label them both as extraneous and you could write no solution.
Oh,
Sometimes you see this symbol for no solution too, it means empty set. I don't know if you've seen that
diameter does.
before, but that's a symbol that means there's no solution. Yeah. Let's try this one. A little bit different, but still the same idea. They've already put everything on one side for us, so it's already equal to 0. We just have to decide what to multiply everything by. First, is this last denominator the product of the two that came before?
Yes.
Yes, it is. So that's good. That's what we want. And what could we multiply everything by to cancel all denominators?
X plus 2.
Xx plus 2. And again, leave it that way, so then you can cross out what cancels. What cancels in the first?
X.
Okay, how about what cancels in the second?
X plus 2.
X plus 2. And in the third?
The entire denominator.
Whole thing. And the rest of it is usually multiplication, sometimes distributive, to figure out what you have. So we need to multiply x minus 3 times x plus 2. So x squared plus 2x minus 3x minus 6. So I foil that out. And then positive 3 times x, that just gives me what? Plus 3x. Okay. What's going to happen on that, on the left side?
Wait, what do you mean? Like on the left
Yeah, on the left side, what's going to happen there? A few things going to happen. Yep.
While simplifying it, both of the 6's are going to cancel out.
Yep.
The negative x is going to be combined with the 3x, and it'll turn into 2x.
And because that constant canceled out, that just got rid of having to do the quadratic formula or really the complicated factoring. We just have the simple factoring. Take out the GCF. So what are my two answers for x?
0 and minus 2 or negative 2.
0 and negative 2.
And both of them are going to be extraneous because it's the exact same numbers that those two are.
Right. Those are what would make my denominator 0. So I can't plug in 0 here. I can't plug in negative 2 there. So that means this problem has no solution. No solution. Okay, so they're both extraneous. Doesn't mean I won't ask you for them. I may still say even though the answers are extraneous, list what they would be. And then maybe I put like a drop down next to on edge elastic, extraneous or non-extraneous, and you pick extraneous. Okay, so there's really no solution to this problem. That works. Any question on that? Let's try this. So this is going to kind of lead us into the last kind of thing we're going to look at. So going back to the Sue getting on a train and taking a car for 30 miles, I want to know what speed she has to travel at to complete the trip in less than 2.5 hours. How is this different than the first question I asked? I mean, I know the first one said 2 hours, but there's a big difference between how this question is asking you to write your answer.
This one's inequality.
This is an inequality, right? So they want to know less than 2.5 hours, not exactly 2.5. Yep.
Also, it's both of the rates. It says what possible rates could she travel. This is referring to not just the car or the train, it's referring to both.
It could be, yeah. It is a little vague how that part's worded. Yeah. So why don't we find at what possible rates could Sue travel in the car? But the way it was worded, I agree, it was a little, it wasn't clear. Okay, so we still have it typed in. But what do I have to change here to figure this out? Yeah.
We changed it to 2.5.
Yeah, we're going to change the 2 to 2.5, so it's going to be a little bit higher for the horizontal line. And I'm still going to start out the same way. What do I want to do with that now? Yeah.
On the intersect.
Yeah, I do want to find the intersect. So I get 34.88. That would be the speed she would have to travel to complete the trip in exactly 2.5 hours. So what speed could she travel at to complete the trip in less than 2.5 hours? Yeah?
Any speed greater than 34.88.
Right, any speed greater than 34.88. So the speed of the car must be greater than 34.88 miles per hour. If it said she could complete the trip in 2.5 hours or less, then I would say, okay, we'll go with greater than or equal to. But in this case, it doesn't say 2.5 or less, it just says less. Any question on that? So that's an example of an inequality. So when we solve graphically, always remember that a graph can have hidden behavior. A good example of that was the first problem. I noticed a little dot, like 1 pixel was lit up just on the very left part of the screen. If I hadn't seen that, I wouldn't have known that there was a third part to the graph. Forgot where I did it. I thought I did it somewhere. Well, there was a third piece to the graph, all the way on the left-hand side. All right, so always make sure that you either zoom out enough to see things that are hidden, or zoom in enough. Okay, when we're trying to solve a problem algebraically, we can't multiply both sides by a variable. That worked with equations. Why wouldn't that work with inequalities? Yeah.
Because depending on whether it's a positive or a negative one, like whether it's going to be like -1 as what it is or +1, it's going to change whether it's going to flip or not.
Right. We wouldn't know whether or not we should be flipping the sign. If you multiply by something with a variable, you don't know. So you can't do that. But what we can do is make a sign chart. So that's where you factor it, and then you make like a number line, and we put like positive on one side and negative on the other. People remember making those at one point before? Maybe. Alright, well, we'll try it.
Is it like for completing the square thing?
No. Not like completing the square. Well, let's see if I'll show you. So the sign chart only works when you're doing a factorable problem. So let's start with the top. What could I do? Well, we've got a few things we need to do. What kind of equations do we have on the left-hand side?
Quadratic.
They're quadratics. So whenever we're trying to deal with quadratics, what number do you always want on the other side?
0.
0. So let's get that equal to 0. So I've got 2x squared plus 6x minus 8 over 2x squared plus 5x minus 3. And what am I going to subtract on each side?
-1.
I'm going to minus 1, but I'm not going to write minus 1. I'm going to write minus 1 like this. I'm dividing two things that are the same. and then I'm subtracting. So is that a minus 1 that I just wrote right there?
Yes.
Why did I write it that way? Why? That's way more complicated than just putting minus 1.
So you can solve the numerators.
What do you mean solve the numerators?
It's they're both, the denominators are the same, so I guess you can solve the numerators.
Right, now we have same denominators, so we can combine like terms. If you just put minus 1, you don't have a like term you can combine. Okay? Common denominator is 2x squared plus 5x minus 3. And be careful when you combine like terms. Everything in that numerator is being subtracted.
Wait, is it plus 3 or minus 3 for the denominator?
Oops, x. That was a 5, forgot my sign in there. That was a 5x minus 3. Okay, so what are we going to get in the numerator when I combine those two together? Let's start with the x squared term. What's going to happen to that?
Cancel.
That's gone. Okay, what about the x term?
1x.
1x. And what about the constant?
It's negative 5.
Nah, negative 8 plus 3, which is negative 5. Okay, now we need to be able to factor the bottom. Top is as factor as it's going to get. It's already linear. How does the bottom factor?
It's 2x minus.
Yep, 2x and x.
They're both negative 6 minus.
They can't both be negatives because then you wouldn't get a negative at
Oh,
the
wait,
end.
no. Plus minus.
Yeah, we're going to need 1 plus and 1 minus. I would try it like that. Okay. And then two numbers that multiply to give us 3.
So x minus 1, x plus 3.
Let's see. So it's going to give you 6x minus 1x is 5x. Perfect. That's how it factors. Okay. Any question on getting to that step? Now we make a number line. Let's start with x minus 5. On the number line, mark your root. So what would you plug into x minus 5 to make it 0? 5. What if you plug in a number smaller than 5 into this? What kind of answer do you get? You get a negative. What if you plug in a number bigger than 5? Positive. Okay, do the same thing for the other two. People remember doing this now?
Yes.
Yeah.
What number do you plug in to make x 0 here? 1/2. If you plug in a number smaller, you'll get a negative. Bigger, you'll get a positive. And one more number line. What value would you plug in to make x make this factor 0? Negative 3. Negative. Positive. Okay. So any question up to that? Right, now, let's put it all together on one number line. So we got negative 3, 1/2, and positive 5. Okay. Well, maybe we don't even need to put it all together. Maybe we can just do it by looking at what we have. If we can, that's one less number line. Let's try it. Let's think about the different kind of things that can happen here. You want that to come out less than 0. Think about, let's start with this. If the top was a negative, what could you have in the bottom and it would come out less than 0?
Positive.
Yeah, the bottom would have to be a positive. Or, what if the top was a positive?
Bottom needs to be negative.
Then the bottom would need to be a negative. So we just have to figure out when that happens. I'm trying to think if we need to combine it. Let's combine it and just see what happens. We might have to do that. Yeah. Okay. Let's look at less than -3. When we're less than -3 in the top, we're in the negative. Less than -3 in the bottom.
Negative.
And less than -3, well, that was the middle and the bottom.
Negative.
Yeah, negative, negative, negative. And what happens if you take, be careful with this, a negative and divide by a negative times a negative. They're all negatives.
Still be negative.
That would still be a negative. So you do have to combine it together. It's easier to think about. Let's see what happens if you pick a number between -3.5. Okay, between -3.5.
Negative.
So negative in the top. Between -3.5.
Negative.
Negative on the left. And between -3.5.
Positive.
Positive. What's a negative divided by a negative times a positive?
Positive.
That's a positive. And what do we know happens each section?
It flips.
It just flips. So now the question is, where are you less than 0? How many sections on that number line are less than 0?
2.
2. How low does this section go on the left?
Below -3. All the way to infinity.
So negative infinity up to, and do we include -3?
No.
No, there's no equal to right there. And even if it wasn't equal to, you can't include -3 for x because it would cause you to divide by 0. So you can't include -3. Okay. Or, what about this section?
-1/2 to 5.
Is that a
I'm
negative
sorry,
one?
not negative, just 1/2.
Just 1/2 to 5. So I tried to do it without combining them. It's too much to think about. I think combining them makes it easier. So that's your answer. That only works if the problem is factorable. If it's not, then you've got to do it a different way. Okay, a totally different approach than solving an equation. I didn't do anything with multiplying both sides to get rid of the fractions. Very, very different approach. Any questions on that? All right, let's try this one. So this is going to be a solve graphically. That's just too complicated. When you see something with a 4th degree, you're not going to be trying to factor that. Okay, if it's that hard, the directions are going to say to solve graphically. Okay, so let's do it. Where should I put all the stuff that's on the left side of the inequality? Where would I put all that in?
Y1.
Yeah, I would put it in Y1. And as I type it in, what symbols am I going to need?
Parentheses.
Yeah, you're definitely going to need parentheses. So x to the 4th minus 3x cubed plus 2x squared
Plus 2. Parentheses. Divided by x minus 2 parentheses. And then you need to set out the y equals to 15.
Yep, we're going to put that at 15. All right, I'm going to fix my window because it's still set to when I did the car problem. I'm going to kind of start with a standard window, except for the y max. I know I need to go to at least 15. So what would be
-30 or -20.
what would be a good y max?
Positive 30.
Yeah, I'd say anywhere above 15. You could go to 30. That's probably okay. And we're going to look for where the curve is above the horizontal line. Well, looks like this curve is in two pieces. It's a cubic asymptote because the degree in the top is a 4 and the degree in the bottom is a 1. That's a difference of 3.
Oh my god, yes.
So it's a cubic asymptote. might look something kind of like this. And as you keep heading to the right, it's going to get closer and closer to that black line, and the same thing on the left. Now, does the bottom part of this ever go above 15? What do you think, Joe? Yeah, because we want to see where it's above 15.
Yes. The bottom part?
The bottom part.
No, not the bottom part.
No, this part, this is completely out of the question here. We don't even need to look at anything with that. We just need to figure out the top part. Okay, so looking at the top part, let's make that a little bigger. What do you think we're going to have to do to figure out where this graph is above 15? Yep.
If you want to have it so the graph that you're looking at, for it, the window would be the y minimum will be 12 for it, and then you'd want to go in closer to there.
All right, you could zoom in closer. I think the window is okay. I think we can see everything we need to see to start to answer this question now. So how do I start to answer this question? What do I need to find here?
Where the maximum of like the inside is, like what the because the thing is, there's a point where it gets like really low, but there's also a point where it gets really high. So you just need to find that point, so that way you can say between the point where it's like really high and the point where it reaches the red line. You can put that as a coordinate or put that as a
Interval.
Yeah.
Yeah. So what would you find? What would you do on the calculator first?
You would go. I would go to table and I would plug in like 2 or like this thing you can't really trust. You're not supposed to trust your eyes in geometry. Oh, then you go to second table set to change it so that way it asks you for the x value.
And if we put in 2, we just saw what's going to happen.
Should say error.
Yes, it does say error.
And so then we know that 2 is the place where like it kind of quote unquote crosses. And then we say the first interval is 2 exact.
Including or not including 2?
Including. Not including 2.
Yeah, you can't. If you include 2, you divide by 0.
Because it said error. And then to 2.22, where we find the first interval.
And how are you gonna find where this interval stops?
It should stop like right. It should stop exactly there because it's going to be underneath it. So you do the second calc intersect thing.
Yeah.
To find the first one.
So find where it crosses.
Yep, the first one.
And we know that you can pick any value from 2, not including it, up to. It's a very small section. It's only like, here's your vertical. It's only from there to there. It's very, very small. So from 2 up to 2.22. That's the first interval. Or
would it be like the square one because it's exactly that?
Yeah, you're right. We can include it. Whoops, I didn't mean to erase that. We can include it because it does have the equal to. So yes, you would want that as a bracket. Or let's just start with the next interval. Am I going to have a bracket when I start my next interval, or a parenthesis? Yeah, it will be a bracket. I need to find the number. And where is it going to stop? Where does the next interval end?
Well, that's hard to say. I think it wouldn't end at all because
It wouldn't end, no.
we have the cubic.
Yeah, it's a cubic asymptote, so if you just keep going further to the right, that point is just going to keep getting higher and higher. It's always going to be above 15. So how do I get this number? What's going to go there? Yeah.
You do intersect again, but at the other point.
Yep. So second calc intersect, and to get the other one, what thing is the calculator going to ask me that's important?
Go closer to the one that you want, which is to the right.
For the, what do we, yeah?
Yes.
The guess. You need to put the guess closer to the right this time. So just put it further to the right. And it gives me an answer of 2.68. So same type of answer as the last problem. Would have been a lot harder to get these numbers by hand if we could even do it at all. So you're definitely going to use a graphing calculator for that. And that's pretty much solving rational equations and inequalities. So that finishes that up. Tomorrow we look at radicals, so square roots, cube roots, things like that. And that'll be a little bit more graphing and solving equations as well. So we didn't have any homework to go over, which is why we got a little bit of extra time today. So let me fix that. I can simplify that. That's really just 1 through 17. 1 through 17. Odd. And then 20 to 22, that's all. And then 24, 28, 31, and 32. Okay, so we'll take a look at that first thing tomorrow. And then we'll finish chapter 4 tomorrow as well. You've got just under 15 minutes left.
I have a question for number 3.